With the ADC up and running, barely up and running, I thought it was time to check the signal path from the input to the output. And since the voltage path is the easy one to put a signal through, that's the one I'm going to test on. Everything is in place here except for R12. With J6 shorted to ground, I get less than 1 millivolt on the VADC pin, so if I actually need to trim the offset of the op amp, I'll add that at a later time. The only filtering that is in place is the charge storage capacitor and the resistor feeding it, coming in at about a 17 kHz cutoff frequency. That is a higher cutoff frequency than I was planning. Turns out anything over about 15 nanofarad in a type C0G603 package is very hard to come by. So I increased R7 here a bit and went with the 15 nanofarad. It's feeding a 5 picofarad sample and hold capacitor, so I think it will be fine. This is the output section from the microprocessor DAC. I'm not using U18 at this time, so it just has a 0 ohm jumper from input to output. The signal goes from the DAC out pin of the microprocessor through a 470 ohm resistor straight to the input of the buffer IC that is driving the MOSFET power modules. So no filtering here at the moment. I kinda want to see what the steps look like coming out of the DAC. To test this, I have an audio signal generator to drive the voltage input line. It only goes up to 60 kHz. Not quite as high as I would like, but it's what I have. I think it will give me some idea of what I've got to deal with. Of course, the signal generator outputs a signal around ground, so I'm only going to get half a sine wave, and I'll just make do with that. I get the 16 sample average ADC value at a 12 kHz rate, and I just send that value to the DAC. So it's going to be a pretty rough looking waveform. Really, I just want to see if there is any output when the input frequency goes above 12 kHz. The top yellow trace is the DAC buffered output. The bottom blue trace is the signal input to the circuit. Once I get up around 6 kHz, there are only 2 DAC updates per cycle, so I have a varying amplitude square wave. Now that varying amplitude square wave will form low frequency signals in the output, frequencies that are not at the input, but my MOSFET power module won't know that. And at 12 kHz it does drop to about 0. But the output does rise above 12 kHz. With some low frequency components in it, and that will be a problem. And then looks to drop around 24 kHz. And then maybe increase a bit. Here at low sweep speeds, can see the low frequencies in the output and how it drops to about 0 at 12 kHz. Not unexpected really. I knew it wasn't going to be that easy. I should have dug a bit deeper into these digital filters before I decided to axe the active filters in the input section, but I didn't. There's only one register per filter that controls the operation of that filter. And as can see here, there are only 2 modes, oversampling and averaging. I don't know much about FIR and IIR filters, but I don't think either of these 2 modes is going to help me much with the anti-aliasing filter. I'm not even sure if this is the correct frequency response for a 16 sample averaging filter, sampling at 192 kHz. I couldn't seem to find much information on just an averaging filter. But if it is, only getting a 12 or 13 decibel reduction at say 18 kHz, that's not really going to cut it. Here, I switched the digital filter to a 4x averaging and doing 625,000 samples per second and 625,000 DAC updates per second. Amazing how much better things look doing 50 times more samples per second. Can just sweep up in frequencies, no aliasing problems. And now the input signal is not being destroyed by the chopped up output, so I'll have a better idea of the input signal that is getting through. I really don't want much above 30 kHz getting through. If I use this as a load on a switching power supply, I don't really want the switching ripple to affect the load level, and still have quite a bit of signal getting through even at 60 kHz. No problems, except at this sampling speed, I won't have time to do much of anything else. I'm going to have to filter the input some more. I didn't make space on the PC board for a proper active filter, but resistance at this pin is about 38 k ohms, and it really isn't too hard to find a spot to stick a 603 capacitor. So I'm going to put a 1 nanofarad cap at the input. That should give me a cutoff frequency maybe a little under 5 kilohertz. Of course, I need to filter the current section too. While I didn't include a spot for a filter, I did put some resistor locations in between op amps, just in case. So I'll replace this 0 ohm jumper with a 3.8 k ohm resistor. Add a 10 nanofarad after it. That should give me about the same frequency response as the voltage section. The yellow trace is the output of the DAC buffer. This time the blue trace is the input to the ADC. By 20 kilohertz, well down in amplitude. Just the faintest bit showing up in the output at 60 kilohertz. So if I can sample at 120 kilohertz or better, should be okay. Then maybe use a digital filter to eliminate anything over say 25 to 30 kilohertz. I'm now running the ADC from the FVOC/4 clock source, which currently is 400 megahertz. I tried to get it to run at 540 megahertz, but I couldn't get it to work. Did get it to operate at 500 megahertz, so can increase the speed a bit if I need to. But at these clocks, that gives me a conversion time of about 330 nanoseconds. Probably 335 nanoseconds for the second ADC core. Need at least 50 nanoseconds of sample time to go with that. Even still, with 16x averaging or oversampling, will give me about 150,000 samples a second. I think that will be plenty. Probably even overkill. But for now, I'm going to trigger the ADCs at just over 120 kilohertz. I'm going to set the filter at 4x averaging, so most of the ADC time will be spent in the sampling state. I'll adjust the conversion delay register to try and equally space the 4 samples in between the 120 kilohertz triggers. And if this turns out to work okay, I can come back and lower the ADC clocks to save some power. I was planning on using an RC filter at the output of the DAC, so I have part locations for them. Even though R65 and C51 here have a cutoff frequency of about 10 kilohertz, the DAC output pin has quite a bit of output resistance. I would expect the actual cutoff frequency to be under 5 kilohertz, somewhat close to the filters I used on the input. Don't know if that's a good choice or not. It's a starting point. With all the filtering, by 4 kilohertz there is a noticeable drop in output. Looks like maybe down 30%. So 3 decibel down is somewhere around the 4 kilohertz mark. By 10 to 12 kilohertz, the amplitude is reduced to maybe 25%. And by 30 kilohertz down to around 10%. Once get over about 50 kilohertz, really getting down into the noise range, so I think I'm good to go. Probably will have to make some adjustments, but hopefully this will keep me from chasing phantom oscillations. With a bit of code in place to read the ADC current values and update the DAC output registers, I've got to give it a spin just to see if things are heading in the proper direction. The load is connected to a 600 watt regular old linear power supply. The meter on the left is reading the voltage at the input of the load, and the meter on the right is reading the voltage from a current sense circuit. Very close to 100 millivolts per amp. I think it reads a bit on the low side. I'll pause here at 600 milliamps. The top purple waveform is the voltage at the load input terminals, AC coupled. The bottom yellow waveform is the drive signal to the MOSFET power modules, AC coupled. I'm starting to see a bit of oscillation in the drive signal, and it's not at the 120 Hz bridge rectifier frequency. And it's also not showing up in the voltage at the load terminals. Very puzzling. I'll take it up to 1 amp. Now this is the start of a problem. This is a great waveform here. It shows 2 problems. One I have a plan for fixing. The other I have a sinking suspicion the root cause is from the MOSFET power modules. In the center of the yellow drive waveform is a nice little ramp. That is coming from the interaction between the fans and the power supply. I have already decided to redo the power supply, so that one I'm not going to worry about. The noise in the voltage and drive signal is a big problem. I do like the fact that the set value is close to what the load is pulling. Of course, these meters are what I use to calibrate the values, but I think it does mean I have some of my math correct in the code. I'll stop here at 2 amps. The noise problem is just getting more intense. That may be as much as 10 volts peak-to-peak oscillation on the voltage terminals. That is horrible. Here, with the sweep set to 20 microseconds of division, can see more of what is going on. I have an oscillation at around 45 kilohertz. I'm quite sure the fact that the DAC data is being updated at 45 kHz is not a coincidence. I'm just surprised considering that the circuit's gain at 45 kHz is so low. While I believe the root cause of this problem is in the MOSFET power modules, I'm hoping I can deal with it in the software, at least make it stop oscillating. Now by the time I get to 4 amps, the 45 kHz oscillations have stopped. They seem to drop out by 3.5 to 4 amps. I'm now pulling enough current to really see the 120 cycle ripple in the voltage waveform, and another very good view of the fan noise making its way into the 3.3 volt supply. The small amount of high frequency noise on both waveforms is not the 45 kHz oscillation. It is the 125 kHz switching spikes from the power supply. Again, I don't know if they are really there or it's just being picked up in the ground noise by the scope probes. I think the safest thing to do is to assume the noise spikes are really there. I'm planning on doing a bit better with filtering on the next power supply. We'll see what it looks like then. At 5 amps, everything looks about the same, and I'm now at over a 100 watt load. 7.5 amps, it's doing just what I want it to do. Looks good. And at 10 amps and over 200 watts, I'm seeing that ripple in the drive signal again. And again, it's not in the voltage waveform. Makes me wonder if it's really there or some interference the scope probe is picking up. It looks to be around 2 kHz. And if it was really there, I don't see why it wouldn't show up in the voltage waveform. As we've seen, can drive the power supply at 45 kHz. So no reason 2 kHz wouldn't show up. The 120 cycle ripple is probably a bit over 3 volts now. Those poor old filter caps. That power supply is so old, I should put some new capacitors in it. But they seem to be doing a pretty decent job. I'm starting to feel a bit of warm air. Nothing feels hot to the touch, so that's good. At 15 amps, everything seems to be okay, and I'm right at a 300 watt load. I'm shooting for a load that can handle 600 watts, so really only at half power right now. I'll take it up to 20 amps. My voltage readout on the load is bouncing around quite a bit. If I remember right, I'm updating the display 5 times a second, maybe 4. I've changed it a few times. And at 20 amps, there's about 5 volts of 120 cycle ripple. The voltage value I send to the display is averaged over about 82 microseconds. So sometimes it gets a value from the peak of the ramp and sometimes it doesn't. That is something I do need to fix. Getting close to 400 watts here, and the air is feeling warm coming off the fans. Power transistor's not that hot though. I can keep a finger on the leads. They're hot, but really cooler than I would expect. I was going to stop at 25 amps, getting close to 450 watts, but nothing is feeling overly hot. I'll push it a bit harder. I'll go up to 30 amps. That's right at 500 watts. The waveforms continue to look about the same. The 120 cycle is getting up there now, close to 7 volts. It's supposed to be a 600 watt power supply, and I think it is. A lot of warm air now. I can still keep my fingers on the leads, but I don't have any temperature sensors on the power transistors yet. And I don't want to melt anything, so I'm going to stop at the 30 amps. I think the first problem to tackle is the oscillations at lower currents, by far the biggest problem at the moment. It may be I need to implement something like PID control in the output code. I'll do a bit of thinking on that. Once I get that under control, I think I need to go ahead and redo the power supply. Really isolate the power to the fans from everything else, and maybe look into some ferrite beads. I would like to eliminate those very short noise spikes. Less noise, the better. So that's 2 big tasks ahead. Thank you for watching.